Welcome to Spring LIB.
Hi, let us look at a situation where we have a fixed axis, and from that fixed axis, we have a small rod AB hanging vertically, and there is another rod BD which is attached with these pins, and then we have rod DE where point E is again fixed to rotate about a fixed axis. Now, the various lengths are AB is 200 millimeters, BD is 250 millimeters, DE is 200 millimeters, and DA horizontally is 600 millimeters. Okay, now if AB is moving clockwise with a velocity 15, angular velocity 15 radians per second, then we are asked what is the angular velocity of BD, and let's say if C is a midpoint, then what is the velocity of point C, where we know that BC is equal to CD. Okay, now so to solve this problem or any of the problems in this chapter, we want to break the motion in translation and rotation and look at the net motion. So we know that A and E are fixed points. So the rod AB and DE are going to move in a circular motion, and that motion is fixed. We can't do anything about it. So the motion of point B will be governed by a translational velocity that will be the net motion of point B. And since it's moving in a circle with a clockwise velocity, this will be the radial velocity omega cross r, and it will point like this, perpendicular to the radius vector, obviously joining A and B. Since it's vertical, this is going to be perfectly horizontal. And the magnitude will be omega times r, which will be 15 times 15 radians per second times 200 millimeters. So this will be 3000 millimeters per second or 3 meters per second. Now this, if this is translational motion, then all the points are going to have the same velocity. So this will have Vt, if we call this translation velocity Vt, then point C will also have this Vt. Okay, now this, then it needs to have some rotational velocity. And for rotational velocity, we assume B to be fixed. Because in the net motion, we know that the net motion of B is just going to be in this circle. So it's going to be like this. Now, the net motion about point D, now we know that D is going to move in a circle where the radius vector is actually pointing horizontal. So now it has to be perfectly vertical. So we can assume any given direction to solve the problem. So let us assume that the omega is clockwise for all of them. So I'll show you that obviously this is a weird assumption to assume all of them clockwise. But what I want to show is that no matter what omega you assume, as long as you are consistent with the conditions of the problem and you follow your mathematics consistently, then if your assumed omega is wrong, then you will get negative of the value, which means that negative of assumed omega, which means if your assumed omega was wrong, then negative of assumed omega will give you the correct omega, which will be opposite. So we'll see how this works out. So if this is clockwise, then net velocity at point D is going to point up. And it will have no horizontal component because it's executing a circular motion and the radius vector is horizontals and the velocity is always going to be perpendicular to the radius vector. Now, what is going to be rotational velocity at point D for a clockwise omega like this? Again, it's going to be perpendicular to the radius vector, so it's going to be perpendicular here, and the magnitude will be omega BD times L BD, where L BD is the length between B to D. Okay. Now, looking at this diagram, we can see that we need to break down this omega LBD into vertical and horizontal components. So if this is angle theta, then we look at our original diagram. If this is angle theta, then we are at a right angle triangle, B, D, and this length is 250. This is theta. So if this is theta, this is 90 minus theta, then this angle is theta. That means the vertical component is omega BD, LBD, cosine theta, and this component is omega BD, LBD, sine theta. Okay, now, so horizontal components need to cancel. So omega BD, LBD, let me just write it slightly more cleanly. So omega BD, LBD, sine theta. So we know that VT plus omega BD, LBD, sine theta has to be 0 because at point D, so this is at point D. So at point D, horizontal velocity is 0, or horizontal component of VD is 0. It's perfectly vertical. So this has to hold. And we know that VT is basically minus 3 meters per second I, it's pointing to the left, plus now omega BD, LBD, sine theta. So since we have already given the directions, let's just put the magnitudes here. So 3 meters per second plus, they are all pointing towards the left, so we can just take the sum of these two numbers. So they are in the same direction, so but they should add to give 0. So 3 meters per second plus, that is the net horizontal component, and net horizontal component is 0. So 3 meters per second plus omega BD. Now if you look at this right angle triangle, then LBD times sine theta. So LBD is just the hypotenuse of this triangle, and we know that sine theta is perpendicular over hypotenuse. So hypotenuse times sine theta will be just perpendicular, so this will be 250 millimeters or 0.25 meters. So then we get 0.25 meters equals 0. Then omega BD we get as minus 3 meters will cancel, and 0.25 will divide 3, which means 3 will be multiplied by 4. So this will be minus 12 radians per second. And notice our assumed direction. Assumed direction was clockwise. So this implies, so I told you, if you assume the wrong direction, you get a negative number, and that gives you the correct direction in the end, which will be omega BD is 12 radians per second anti-clockwise. So like this. Now what can you say about omega at the point D? Now we know that the net velocity at point D is, so this is not asked in the question, but I'm just trying to give you a good physical picture. So net velocity at point D, we have assumed it to be vertical, and that is going to be omega BD LBD cosine theta. Now since we know that omega BD from our assumed direction is negative, this will be minus 12 radians per second, and then LBD cos theta, whatever be the value, like I don't care about the value right now, although you can easily get it from this triangle. But anyways, so this will be like 600 millimeters, because this directly below, the point directly below B is 600 millimeters. But anyways, so we don't need that, so we won't find it out. Or let me just write it. I mean, no harm in finding additional quantities, right? So this is 0.6 meters. So this will be 12 6 are 72. So minus 7.2 meters per second. Now again, it's negative of your assumed direction. So then that basically means that your assumed direction was wrong, and then VD has to be pointing downwards. So 7.2 meters per second down, or 7.2 meters per second minus j. So this tells you that omega at point D, you can find that out as well now, because now you know Vd, so it's 7.2 meters per second divided by the radius dE, which is 200 millimeters, so 0.2 meter. And the direction, again, negative of our assumed direction, so it's going to be anti-clockwise now. So I also found out omega. This is not asked, but I'm just solving this so that you get a good idea, and in an exam or in any real situation you are solving this problem, you can always solve it like this. So dividing 32 by 72 by 72 by 2 is 36, so 36 radians per second anti-clockwise. That's omega about the point D. So I also figured these values out, which you didn't really need, but you have them now. Okay, what we needed was velocity at point C. So velocity at point C, right? So what is point C? Point C is at the midpoint of rod BD here. So if we, so net motion, so this is always going to be translational velocity plus rotational velocity in the vector form. And we know that translational velocity is same for all the points. And we figured out that this was 3 meters per second to the left. And then the rotational velocity at point C, we have figured out that the velocity is anti-clockwise. So this is going to point like this. And if this angle is theta, this will be 90 minus theta. So this will be theta. So the components will be omega. Now this time we have LBC, only the midpoint, or we can just write it as LBD over 2 because we have been told that it's midpoint. So LBD over 2. Since this is the vertical component, will be omega LBD over 2 cosine theta, and the horizontal component will be omega BD LBD over 2 sine theta. Okay, so now the net velocity will be sum of these two. So let's just write them down. So velocity of point C is minus 3 meters per second I, plus, it's pointing towards right here, so it's going to be plus I, and omega BD we have already figured out. Omega BD, actually we even know omega BD LBD sine theta because from, but let's just use the figured out value of omega, which is 12 radians per second. So 12 radians per second. Then LBD sine theta, we have figured out LBD sine theta was 250. So this will be times 125 millimeters. And then I. And then in the vertical direction, it's pointing down. So we have minus. Then omega LBD cos theta. So I already told you that the distance, if this distance was 600 millimeters, then LBD, if this was theta, then LBD cos theta, since cos theta is base over hypotenuse, so hypotenuse times cos theta is going to be the base. So this will be 600 millimeters. So an LBD cos theta over 2 will be 300 millimeters. So this will be minus 12 radians per second omega BD LBD cos theta over 2, so, which is 300 millimeters times J. So now this is equal to, so 125 millimeters is 0.125 meters. So 12 times that will be 12 5s are 60, 12 2s are 24 plus 6, 30, and then 12 1 is 12 plus 3, 15, and then there will be a decimal point, so it will be 0 0 5. After the 5 there will be decimal point, and then there will be 1 on the left of the decimal. So this value is going to be 1.5. So this is 1.5 meters per second. So minus 3 plus 1.5, so you left with minus 1.5 meters per second I, And then this value 300 millimeters is 0.3, so it's minus 3.6 meters per second J. So this value is 3.6 meters per second J. So minus 3.6 meters per second J. This is going to be the velocity of point C. So we have figured out velocity of point C as well. So remember, to solve any of these kind of problems, you just break the motion in translation plus rotation for the rigid body and just equate the components of net motion, and then you will be able to solve any of these kind of problems.